Group A's presentation on Haidinger's brushes focuses on S-cone waveguide theory. We will explain the concepts behind the theory and how it successfully explains the Haidinger's brush phenomenon. While no theory has been proven, by the end of this presentation, we hope you agree that S-cone waveguide theory is the most logical explanation.
So this presentation is going to detail the short cone or blue cone waveguide dichroic theory of Haidinger's brushes. Haidinger's brushes are an entoptic phenomenon where an individual will perceive the polarization of light. It appears as a yellow bow tie that's either perpendicular to the angle of polarization, or it appears as a blue bow tie that is parallel to the angle of polarization. The size of the Haidinger's brushes are proportional to the size of the macula and attributed to dichroism of the macular pigments. The oblique rays of blue cones are what produce this dichroism. People with strabismus can typically have eccentric fixation and can be trained to view objects. Typically, the fovea has a greater resolving power than the retina. Haidinger's brushes can be used as a diagnostic test for macular degeneration and macular edema. They can also be used to ensure functioning of the macula preoperatively in some cataractus patients.
Anatomical variation and eye dominant determination. The brush size is larger than the fovea and it is centered on the macula. Because of this, it must originate from the macular area surrounding the fovea, which contains blue cones. For most people, the shape of the fovea tends to be more oval than round and elongated in the horizontal meridian. In the dominant eye, the rotating pattern has been shown to be more symmetrical around a more circular, blue, cone-free fovea, whereas in the other eye, the dark axis is generally more diffuse in the vertical direction. These differences of blue cone distribution among the eyes may be the source of the appearance of the two patterns. The dominant eye produces a more regular, less diffused brush pattern containing a darker center when exposed to polarized light. This blue cone pattern is thought to enhance communication with the brain, establishing eye dominancy. 2/3 of the population is right eye dominant with a more circular blue cone distribution around the fovea in the right eye. Dichroism. Dichroism refers to any optical device that can split a beam of light into two beams with differing wavelengths. This includes both mirrors or filters. The cylindrical geometry of the foveal blue cones produce dichroism because a small number of these cones located in the macula have a circular arrangement. This arrangement differs from the other cones in the macula and the rest of the retina. The splitting of a beam of light produces two beams that would appear as two different colors. Typically, these are blue and yellow. These are then perceived proportionally to the diameter of the macula.
Blue cone orientation. In the foveal pit, light can hit blue cones without being blocked by the inner retinal layers. This allows light to hit cones at a wide range of angles. Fresnel's laws say that the outer segment of blue cones oriented parallel to the light source receive more oblique light than those that are oriented perpendicularly. The intensity of light hitting cones located at any angle in the fovea can be calculated using the following formula on the screen. Assume that the incoming light determines the x-axis. Therefore, the parallel cones will be in the x-axis of the fovea, perpendicular cones will be on the y-axis, and oblique cones are in everything in between. The light and dark bands of Haidinger's brushes. Cones that are parallel to the incoming light get activated and produce a light band pattern. Cones that are perpendicular to the incoming light do not get activated and produce the blue-dark patterns. Cones that are oblique to the incoming light produce a band pattern that is intermediate to the light and dark patterns. The intensity at any given point can be calculated by determining the angle of cones from the parallel axis and plugging it into the following equation displayed on the screen. As the polarizer rotates, the angle of cones parallel to the axis will change and different cones will get activated. These spinning light and dark bands will produce the effect of Haidinger's brushes. This is an example of what we just talked about. In the first picture, the incoming light is coming at 0 degrees, and the cones that are parallel to the light produce this light band pattern. The cones that are perpendicular to the incoming light produce this dark pattern. The other two pictures are the same, except for the light is coming in at 45 degrees in the second picture and 90 degrees in the third picture.
Previously, we talked about the light and dark bands of Haidinger's brushes. Now we're going to talk about the contrast estimation of the patterns. Total blue intensity is estimated by evaluating number 1, the polarization independent guided part, and number 2, the polarization dependent unguided oblique part. Number 1, the polarization independent guided part reaching the fundus is 4 times larger for blue light than red and green lights, better preserving polarization. For red and green photons hitting the center of the fovea, the oblique ray contribution falling on the red and green outer cones is reduced, reducing contrast to less than 1%. Number 2, polarization dependent unguided oblique blue ray path is twice as long as red or green ray paths. As a blue cone becomes isolated in a cluster, its cross-section is estimated as twice that of red or green cones in the cluster. For these reasons, the origin of Haidinger's brush patterns appears restricted to the blue-violet part of the spectrum.
In summary, Haidinger's brushes are significant clinically in that they can be used as a test for macular degeneration and macular edema. Most patients that we will be seeing will have more circular blue cone distribution around the fovea in the right eye. Yellow and blue beams of light are seen because of dichroism. Light hits blue cones at a wide range of angles. Blue cones that are parallel to the light source receive more oblique light. A light and dark band pattern is produced based on the orientation of the cones. Many objections surround theories involving refractions of intraocular media, radial fibers acting as an analyzer, and reflections of rays falling on cones. This theory is one that successfully explains blue brushes as a positive phenomenon and fits with current knowledge of dichroism.
And then for our references,